Hey everyone, and welcome to Dr. Abu Artin Academy channel. Today we are going to discuss part 4 of the descriptive statistics as part of the biostatistics subject. As discussed in the previous video, we can use the time plot or the line graph to compare two sets of data, okay? If I have two sets of data like these two sets of data, the data for the cases which get infected or diagnosed as influenza, and the other set of data which is related to the death related to the influenza case. So we have two sets of data. This data for the cases diagnosed as influenza and the death cases which is due to the influenza. Okay, both of them we are using the same x-axis or the timeline for both of them, which is from week 1 to week 17 on x-axis, from week 1 to week 17. But as we can see here, and as we have mentioned in the previous video, the y-axis for the cases diagnosed as influenza starts from 0 and end up with 10,000, because the cases which was diagnosed as influenza start from 36 up to 8,000. So the suitable or most appropriate scale for them, it is from 0, it should be smaller than the smallest one or smaller than the minimum is 36, so it should be smaller than the minimum and greater than the biggest figure or the maximum reading which we have. So smaller than the minimum, which is 36, it will be 0, and up to 9,000 or 10,000. In our case it is 10,000. And for the death cases, start from 0 and up to the biggest number, which is 738. So we start our scale from 0 to 800. This scales, it cannot be selected or choose randomly. There are some things which we have to consider while we selecting the axis. So whether we can stretch the axis or compact it, or how we can identify or specify the maximum value of the x-axis or y-axis and the minimum value, a starting point, whether to start from 0 or start from the minimum value or very close to the minimum value, or we have to start from 0 for x-axis and y-axis. So all this we are going to study in the next slide. On this slide, it's clear that the scale matters. The scale of x-axis, it matters. The scale of y-axis matters. So here, if we look at x-axis, the timeline here, the time axis here, the x-axis starts from 1940, 150, 60, 70, 80, 1990, and 2000. And here also start from 1940 up to 2000, to the same range. The range start at 60 years, start from 1940 up to 2000, and here the same start at the same end. But look at the scale which we have here. Here, the scale every 2 centimeters is 10 years. And here, if we look down here, every 2 centimeters, we have 20 years. So here 20 years, okay? For one step, it is 20 years. The same step here, it is only 10 years. So that's why this x-axis is stretched. If it is stretched, so see the graph, how it looks like? It looks like a straight line because that's been stretched horizontally. If we look at this one, it is not horizontal as this one, okay? The second thing here that we have the y-axis as well. So y-axis, every 1 centimeter represent 50, starts from 50 up to 250, okay? So here every 2 centimeter represents 50. Here every 1 centimeter represents 50. So that's why also it is stretched, okay? The second thing which we have to consider also here, that we started here from 0. Okay, the x-axis we started from 1940 up to 2000, which is the same here and same here. But here we started from 0. Do we need all this area which doesn't have any single measured data? It is empty, blank. So why I should have this and make this graph congested or compacted, so I cannot read all the details or get all the details from it. So it is wise to eliminate or rid of or remove this part. So we can start, for example, from 100 or 120 or 130. So as we have taken the high school or in the secondary school, that the graph, if this is the graph page, our graph should represent at least 50% of the x-axis, if this is the x-axis, and 50% of y-axis. It could be 70 or 80 or 90 or 65, but at least should be 60 or 50% minimum. Okay, so here, if we look at this one, so here we have almost around 50% blank, which is not acceptable. The same thing here, we have 50%, almost 50% is blank also. Here also we have 50% blank. So stretching the axis, it could mislead us or give bad impression, because the photo worth thousands of words. This is an English say. One photo, just see the photo or the drawing or the graph or the comics or whatever, or it means or equivalent to thousands of words. No need to speak, just show him the photo. It's self-explanatory. It may give more than what thousands of words would give. Okay, so the picture worth thousands of words. Okay, but there is nothing like hard numbers. If you just have the table, 1,000 cell and or 100 cell columns and five columns, each one of them 500 cells. So it will be very, very complicated. But if we represent them as a graph or line graph or a time graph, it will be very easy from the first impression, from the first spot, to recognize whether the trending is rising or it is declining, or they are going together or they are deviating. So we can have many conclusions to be withdrawn instantly in case if we have graph, rather than if we have a table or have hard figures or hard numbers or hard data. Okay, so to be more professional, we look at this graph, which better than this stretching one and this one. Okay, because both of them are stretchy graphs. So here we start from 120, so just we have a small gap here, but it will give us impression how it looks like. All the numbers will be clear. The curvature here or the change of the direction is clear for every and each point. Okay, and the scale also here should be reasonable. Okay, so this graph, just by selecting the proper or the most suitable scale, we have a better graph than this one and then this one. Okay, so this graph is better than the other two graphs which we have here. So we can say that the scale of the graph matters. Scale means the deviations which you have here between each step, the deviation, and also how big the distance between the deviations. So we can jump here from 0 to 100, which is one scenario, or we can stick to the same scenario but make the distance bigger, so it will give different presentation. So we have to make sure that our graph is representing the very nice and reflecting all the data in a clear way. Coming to the frequency distribution. Before explaining what's written here for the frequency distribution, it is good to remind you what is the frequency itself. If we look at this table, which we have here, we have the class of between 50 to 59. How many numbers of people or elements are there? 1. The class or the category of 60 to 69, we have 7 people here in this category. The class of 70 to 79, we have 4 people. So this is called frequency. Okay, so how we can group this data to make them into classes or categories? So how we can make them? For example, if we look at this example which we have here are grades for 15 students. So one of the students scored 88, 48, 60, 51, and so on up to 60, 73. So we have a wide range, around 15 students, and we need to group them, to put them into groups in order to deal with them or to represent them in a graph. So how we can group them? So first of all, we have to look at the minimum number which we have. If we look at the minimum number here, which is 48, and the maximum number is 97, okay? So the range which we have here is 97 minus 48, which is almost around, I think, 49, okay? 49, so we are talking about tens. 10, 30, 10, 20, 30, 40, 50, tens. We are not talking in hundreds. I don't have numbers here, 450, 760, 800 something, 900 something. So we are talking about tens. We could end up with a problem. We are talking about units, 2, 4, 6, 8, or tens, 34, 43, 57, 98, or hundreds, or thousand, 1,200, 1,900, or tens of thousands, or millions. It depends. So the category will depend on the maximum and the minimum. So here we are talking about tens, 40 something, 90 something. So our deviation will be tens. So here the difference between this and this is around 49. We usually, when we categorize the data, we can categorize them into 3 category, 4 category, 5, 9 category. But we cannot go to up to 20 or 30 categories. So it should be something around 5, 6, 7, within this range. So if I divided the difference between the biggest number, the maximum number, and the minimum number divided by 10, I'll get 4.9, which is almost 5. So I have 5 categories, and the starting point, so this is the starting point, and then first category, second category, third category, fourth category, fifth category, and so on. So I can have up to 6 categories. 5, if I divided this 49, the difference, the range, this called range. Range is the difference between the biggest number and the smallest number. If we divided the range by 10, I'll get 4.9, which is has to be rounded up to the higher number, which is 5. Then I add one more, because the first one I'm not counting. I'm counting the gap between the category. This first category, second category, third category, and the fourth category. So I should have 6 categories, okay? So in order to break this data down into categories, or put them into classes, we can call them classes. Sometimes we call them pins. So classes, not school classes, class, category 1 or class 1, class 2, class 1, class 2, and so on, okay? Put them into classes or categories, or sometimes we call them pins, okay? Pins, okay? So categories or classes or pins, it doesn't matter for us. So how we can break these numbers into category? We get the smallest one, and we approximately get how many ranges. So now we agree that we are talking about tens, so we'll take the category range, which is 10. 10, there are 2 ways to write these tens. So how we can split them or write them? If I'm talking about something which cannot be broken down or split, like the head count, the number of people, I cannot say I have 4.2 people, or 14.9 people, or 73.1 people. I have to say integers only. I have to talk about integers. 2, 3, 7, 17, 92, but not point something. There is no decimal, because we are talking about the people, or animals, or plants, which cannot be split, okay? So if we are talking about cases like students, we cannot break them down. So we can say, for example, we'll start from 40 to 59. These are 10 numbers. We said each category, each class will be 10 elements, okay? 10 elements. So this is 9 elements, right? No, sorry. It is up to 49, not 59. 49. So this 9 elements. No, it is 10 elements, because 40 is counted. So 40, 41, 42, 43, 44, 45, 46, 47, 48, 49. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, because this is the first one, it is 40. Second, 41. Okay, third, 42. So always the third will be 42. So the ninth would be 48, and tenth would be 49. Okay, so these are 10. So this category has 10 elements inside it. Okay, I can say from 40 to 49. The most important thing, I should not have any overlap between this category and the next category. For example, if I said I have 40 to 49, and then I said here from 49 to 50, for example, okay, or 59 from 49 to 59. So what is the problem here? The problem, I have 49 here and 49 here. So if I have 49, exactly 49, so shall I put it here under this class or this class? Some people will put it here and some people will put it here. Maybe you have two different groups are carrying out the experiment, or two different groups are working in two countries. So if we don't have this clarity in all our experiments or practices, so we'll do this mistake. So our data will be unreliable, totally unreliable. Because 49 here, 49 here, we are not sure which category is right and which category is wrong. Maybe here we'll have 5, then here we'll have 7. Someone will say, okay, there are many items included here which is supposed to be here, so there should be 3 only, okay, and those ones should be 9 if we move this item. So the whole data will be unreliable. We cannot rely on this data, okay? So we have the first rule, we should make sure that there is no overlap, no chance for overlap. For the case of the people or the animals or plants which we cannot split or have decimal, it is very clear cases. Because you write from 40, for example, to 49. From 50, next one. So here start with 0, to 59, okay? There is no overlap. Here from 60 to 69 and so on. There is no overlap. 49 and here we start with 50. So if it is 49, it will be here 50. If it is 49.2, there is no men or animals or plants, which is 49.2. It has to be integers only, okay? So in such cases, it is very, very clear that we don't have overlap. But if we are measuring the height of the people, for example, I say I have a person, his height is from 159 to 169, okay? So his height is greater than or equal to 159 and it is less than 169, okay? Here I can say 169 also and x, okay? 179. So the problem here, I have 169 shown twice here and there. So how can I make sure that it is not repeated here? I can make sure that it is not repeated only by one thing. That here I should have x is less than but not equal, less than 169. So it should be only less than, not equals. So if I have exactly 169, it has to be here. If I have 168.9999, it has to be here. So up to 168.99, it will be under this category, okay? It will be under this category. Once it reaches 169, it has to come under this category because x here equals this amount. So here we have decimals. The height of the people could be 169.1, 169.7, and so on. So it can take any value. In this case, we have to make sure that we have equal to or we don't have equal to, but we have to make sure that there is no overlap. So again, here, if we have x takes between 160 to 170. See, if you notice here, we are not saying from 160 to 169, because 169.1, 0.2, 0.3, 0.999, it has to come within this category. So here we have to repeat the same number here and there. But the only thing which we have to consider, whether x is less than or equal to, or x only is less than 170. So it could be both of them. So here x is greater than or equal to 160 and x is less than or equal to 170. But if I came to put it here, I have to put it here x less than only. I cannot put equals to because equals to came here. To avoid this confusion, always or not always, oftenly, the first one will be put as x greater than or equal to 160 and the second one will be put x is less than without equal to, okay? And to repeat the same sign here, okay, we can put here greater than or equal to 170 and here less than. So the next category will be equal to 180, x greater than or equals to, okay? And x less than 190 and so on. So the last one will not be with equal sign. So we can repeat it here. So here it is up to 179.99999. Once it reach 180, it has to come in this category. So there is no overlap. In some cases or in some books, you will find this like 160. It's written like this: 160, 170. Okay, or with the bracket, or with dash, or with comma. And you find the first bracket, it is square bracket. The last bracket will be parentheses, this curved bracket. Okay, so if the square bracket means equals to, so 160 equals to our numbers, it can take any value between 160 and 170, but 160 is included. But this parentheses, the curved one, it is not included. So it's like this one. Okay, so it is the same meaning. So here x greater than or equal to 160, which is under this square bracket, comma, or x can go up to 170, but 170 itself, it's not included because it is under this curved bracket or parentheses. Okay, I hope this one is clear. So here, how we can get the frequency if we have a group or set of data, how we can get the frequencies of them. This is an example, external example. Okay, so here, if I want to get the frequency distribution table, I want to draw it. Okay, so I have to group the data. How I can group the data? As we explained in the previous example, we have to check the smallest number and the biggest number, the minimum number in the range and the maximum number in the range. Okay, so the minimum number in the range here, it will be, so the smallest number here is 58 and the biggest number is 93. So so here we are talking about tens. So automatically we'll know that, okay, we'll take one number which is smaller than 58, which will be 50. So we can start from 50. If we don't know how many category approximately, we can have this number minus this number. So 93 minus 58, it will be around, I think, 37. 37 divided 10 equals 3.7. So we'll have approximately 4 ranges plus the initial one, the first one. So we'll have 5 categories. So if you look here, we have 1 category, 2 categories, 3 categories, 4 categories, 5 categories. Because this is the first one. From here we arrive to 4 plus the first one. So we have 5. Always we are adding 1. But we don't need actually to look at this one. Just we can put the range of the data in the order and it will be clear for us. So here we can start from 50. So 50, and we said that will depend on tens. So from 50 to 60. But because this are the number of students, we don't want to have overlaps. We cannot put 60 here and 60 there. So in this case, we'll put from 50 to 59 because there is no 59.99 or 59.2, 59.1. It is head count. It has to be full or integer, full number. Okay. Even in the data itself, there is no decimal places. Okay. So all are full numbers. So I can put between 50 to 59. I don't have 59.2, 59.7. Any decimals in the set of data which I have, so I can use the full numbers. Okay, in this case I don't need to have overlap. I should not have 60 and 60 and what greater than equal to or greater than. No, I can have here only the full number because there is no overlapping between them and there is no decimal places. So the first one will be between 50 and 59. How many number between 50 and 59? I have only this number, which is 58. So 58, I already put it here, so I put 1. So the frequency here is 1. This tally means like if you have some sticks and just put the sticks, then you can count. And here is the number 1. Okay, so between 60 and 69. So let us erase this one. So between 60 and 69. So I have the first one, 2, 3, 4, 5, 6, 7 number. So I have 6 number. When I come to put the tally or to put them in the table, how shall I do it? Let us do it again. Okay, so 1, I draw 1. Okay, let us put it here outside. So I put 1. Another one, I put another 1. 1, 1. 1, 1. So I have now 1, 2, 3, 4. Okay, and this one 5. When I come to 5, I make cross line. I don't draw 5. So 4 and the fifth one will be crossing. Okay, so when I see this shape, it means it is 5, complete 5. Then I find 62, additional one, so it will be 1 more. 61, it will be 1 more, so 7. So when I see this one, from the first instant I see 5, 6, 7. I no need to count all the sticks or the numbers or the tally which I have here. Okay, so the same thing has happened here. So the range of 60 to 70 of 69, what we have, for 1 we draw 1, again 2 we draw 2, 3 the third one, 4 fourth one, 5 fifth one. Okay, and then 62 one more, 61 one more, so total 7. I wrote here frequency 7. So this is the frequency how many times this range or this character or this class it repeated. Okay, how many times it appears, how frequently it appears, appearing 100 times, 2 times, 1 time, 7 times. So this is called frequency how many times this class appears. The class between 60 to 69 it appears 7 times, the class between 70 to 79 it appears 4 times, and so on. One also of the important tips here, that before we start grouping this set of data into groups, we have to count them to make sure how many they are. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 number. So when I count the tally here or the frequency here, I have to add the frequency up. So 1 plus 7 equals 8, plus 2 equals 12, plus 4, this 4 equals 16. So 16 and there 16, so I did not miss anyone. This is just double check to make sure that we did not forget or miss out any of the numbers, okay? In this slide, we are going to discuss the most common distribution shapes, okay? As we can see here, this is the first one, okay? So in this one, we have the grades, equivalent vocabulary scores to the scores which is scored by the student, and this is the percentage of the 7th grade students. So I have majority of the students up to 12% here, 12%, maybe 15%, maybe here 13%, also 12 or 13% of the students scored in the range of, here we can say 4.5 to 9. So the majority of the students are within this range, but this is not our point. So our point here, we are talking about symmetry of the graph or the distribution of the shapes. So the most common distribution shape, the first one which I have is symmetric. Symmetry, as we have taken many times before in the high school and elsewhere. So symmetry means similarity that we have. For example, if I have a triangle, so I can say that, okay, I have symmetry between this shape and the red shape and the white shape. There's symmetry between them. Also, I have a kite, for example. I have symmetry, okay, between this side and the other side. If I split them into triangles, so I have here this shape, this side and this side. And the same thing also, this triangle and this triangle as well, okay? So symmetry means the two shapes are similar to each other, like sort of a mirror, but it's not exactly a mirror, but sort of a mirror, okay? So here, we said symmetric distribution. What does it mean, symmetric? There is symmetry, like approximately like a mirror. So we should not look at this bars which we have here, this bar and this bar and this bar and this bar. No, let us draw a curve almost touching the edges. It's not must to touch all of them. So here, so we can see if we look at the shape which we have now, so you can see that almost we have some similarity, okay? If I draw a line here, we can say that this shape, this side, okay, this side, it is almost similar to this side, okay? So that's why we call it symmetric distribution. Symmetric distribution is a distribution. A distribution is symmetric if the right and the left sides of the histogram are approximately mirror images, because in most of the cases, or in rare cases, you'll find them exactly mirror, but most of the cases they are approximately only mirror image, okay, to each other. We did not discuss the histogram in detail, but just to remind you of what we have mentioned earlier, that histogram is like bar chart, but they are closer. Each bar is adjacent and touches the next bar, okay? There's no gaps between them, okay? There is no gaps between them. So all of them are touching each each other, okay? Attaching to each other. That's why it's called the histogram, because you may find the word of histogram here and you get confused. Okay, so histogram is like bar chart, but this for continuous data, where the bars attach each other and there is no gap between them. So now we understood when the distribution will be symmetric if the right and left side, okay, if the histogram are approximately mirror. From the bar chart, sometimes it's a little confusing. You cannot identify whether they are symmetric or no. You look at this one, this high, this one is low. So it is not simple. So better to draw a curve like this, okay? And see how the curve look like. So if you look at the curve here, you can see easily that the curve is almost splitting it into two halves, okay? This one half and the other one the other half. That's why we call it symmetric distribution, okay? We have another type of distribution which is called the distribution is squeezed. Squeezed means like squeezed, okay? You can, in order to understand it or to memorize it, okay? It is just a little tip to memorize it. Skewed means like squeezed. You can remember it with the word squeeze. So it is not big. So here I can draw a line also here, and you see what happened. So I can draw the line here. So it can be this shape. Let me draw it again. Okay, I'll find that I have big area, okay, and then I have like a tail. See, this is like tail. This tail this area is big, and this one like a squeezed area. We compressed it, we squeezed it to become like a tail. Okay, so this is the skewed area. A skewed area means the area. Okay, let's take the definition better in order not to confuse you. So here, if we draw this curve here, okay, so we'll have the tail, okay. We'll have the tail here. So this tail toward the right or the left. So the big area toward the left and the tail to the right. So we are looking at the tail. Tail to the right is called skewed to the right. Skewed to the right means the tail to the right, okay? If we say the skewed to the left, the tail to the left. Some people are given some little confusing definition. They said, okay, if you are looking at the right and left, okay, they said, okay, look at these numbers which we have here on x-axis. These are the big number. So here we're moving from 4 to 5 to 6 to 7 to 8. So numbers are increasing. They said that, okay, the numbers which are increasing, here, see, the distribution is skewed to the right. If the right side of the histogram, this is the right side of the histogram, the side with larger value. Larger means here 4, 5, 7, 6, 7, 8, not 0, 1, 2, 3, 4. So this is the side with the right side, okay? The right side, the side with the larger value extend much further. So if we looked at the side of the large number, 3, 4, 5 numbers are increasing, you will see that, okay, this big number, the tip, okay, this number is covering only almost around 3 or 4 bars only, okay, from 0 to 4. But the bigger numbers, 4, 5, 6, 7, 8, almost all of them are dropping down, okay? See, the tail is going down starting from here, from almost 3 or 4. So the biggest number, not 0, 1, 2, 3, the smallest number, the biggest number, okay, are more extended, okay? So the area which it is dropping down, it is longer than the area where we have the smallest number, okay, the high one, okay. But for simplicity and the easy purpose to memorize, there are two things to memorize. The first thing that we have to draw a curve here, okay, touches the biggest one. So these are the biggest one, touch them and then draw a tail for them, okay. If the tail, this tail to the right, so it's called skewed to the right. That's it. If the tail is to the left, so we are calling it skewed to the left. That's it. Just to draw the curve and see the tail. Where is the side of the tail? Some people are given some different tips or tricks how to memorize them. I'll give you also one example of how to memorize and not to confuse between the skewed to the right and the skewed to the left. See, I have these two graphs, one of them like this, okay, and the other one like this. So where's the tail? The tail here to the right, okay? So this is called skewed to the right. The tail here is to the left, okay? Some people are giving other different examples or other different way to memorize it. They are saying, okay, for this shape, okay, if we put our right hand here, like this hand, see, this is the hump, okay, of the right hand. It is going like the hump of the histogram, okay? It's going up, okay? The rest of the hand is going up and the hand is going down. So this is the right hand, it will be right. But as I told you, just look at the tail. If the tail to the right, it is skewed to the right. If the tail to the left, it is skewed to the left. As simple as that. It is not always simple that we have symmetric distribution, okay? Or we have skewed to the right or skewed to the left, okay? Sometimes we have complex multi-modal distribution. It has more than one mode. So here, if you look at this one, okay, you can find this little bit skewed, and also you can see it is symmetrical, okay? You cannot judge on it, and also the same thing here. So, and all together are one graph, so we cannot say whether it is symmetric or skewed to the right or skewed distribution to the left. You cannot judge on it. That's why here it says that not all distribution have a simple overall shape, not like this one. And make sure that if you have one like this one, I did not go up and down with everyone, just the profile, the overall profile, okay? Not all the distribution have simple overall shape, especially when there are few observations, okay? If I have 2-3 observations, only like this one, 4 observations, it will be very difficult actually to get to say that the distribution is symmetric distribution or skewed distribution to the right or skewed distribution to the left, and so on. Okay, so in some cases we have complex multimodal distribution.